So yeah, so it looks like Eric has been at Qualcomm for 16 years. That's a long time, Eric.
Feels like it sometimes.
It'll be great, Eric, as you kind of get started. It'll be awesome for students if they could hear a little bit of your background and sort of like how you got into this space and sort of how you've seen actually the evolution of the DSP from what it was being used to, today you hear about DSPs and everybody gets caught up in all the new buzz around the machine learning stuff, but then often people don't tend to realize there's actually a long legacy for all these things, right? So I think if you can share a little bit of that perspective as you're going through your material, that'd be awesome.
Yeah, sure. So,
oh, and one more thing, Pete, add something in because Pete is the one who introduced Eric to me.
Yes. So I met Eric after I gave a talk at I think it was the Embedded Systems or Embedded Vision Summit, sort of a quarterly get together in Silicon Valley of a lot of hardware people. And what I was saying was, hey, what we really need for machine learning, like people are building all of these really fancy NPUs with floating point and things like that. And I was there saying, hey, all we need is 8-bit integer dot products. Give me 8-bit integer dot products, and that will be, the bulk of our computations. And, give me that for like, low power, low latency, and I'll be super happy. And after that, I actually got approached by some people who worked with Eric in the Hexagon DSP side, and they were like, huh, that's interesting. We've got a lot of 8-bit multiply adds in our DSPs already. Do you think we could use those for sort of machine learning? And that actually led me to a kind of a pretty, sometimes I've heard somebody talk about the only way that things get done in Silicon Valley is through a conspiracy of engineers. So me and Eric essentially sort of sat down together and like hashed out how we could actually prototype running, I think it was MobileNet on one of the Hexagon high-end compute DSPs. Yeah. And thanks to
Inception v3, and we had a demo app.
Oh, Inception v3, even before MobileNet, yeah. And it worked really, really well. It was very fast. It was very, comparatively low energy usage. And the nice thing was it was already shipping in the Pixel 1. So we not only had like a nice hardware demo, we actually had a hardware demo that ran on shipping hardware. And that was really the start of like a really fruitful collaboration between Google and Qualcomm on this stuff. But it was all down to Eric actually, putting his head down and really impressively putting together this, this demo application and getting some really impressive numbers. And yeah, ever since then, I've been in awe of Eric's, not only optimization ability, but ability to kind of do the system integration side of things, not just the inner loops, but actually trying to plug everything together and make it work, which you'll learn is actually way rarer in a lot of ways, more valuable than just being able to do the core inner loop stuff. So yeah, I'm excited to see what Eric is going to talk about today.
Yeah, so you asked about my history, and I think that's actually a good, Pete just had a good one of the, things that went on, which is you got to be in the right place at the right time. And so, we had designed an image processing accelerator, and it is used for that. Like if you go get, if you have your, your Pixel camera, it does a lot of its computation on the image processing accelerator, but it kind of just happened to be that we had the right instructions for also doing these dot products, right? 8-bit dot products as a part of that image processing accelerator. And rewinding even further back, the way I got the way we started Hexagon DSP was that we were in the right place, which turned out to be Austin, and we were, you know, available for doing a project, and we had the right vision, and we're able to get something done that worked really well. And so if you're in the right place in the right time and you can get the job done, then you can be very successful. And that's, so it's a little bit of skill and a little bit of luck. And when you get both those together and you get the right opportunities, it's you can have a lot of fun. So that's,
I think that's the key thing, is like making sure you don't miss the opportunity.
yeah.
I think like one of the big key things, and I think that's an important thing, is very often we have something set in our mind and we kind of want to chase that thing, but then like new opportunities come up. And one of the pitfalls that I do find with students is that they kind of thought they're going to do something, so they want to stick with it.
Mhm.
I'm like, no, the best thing you can do for yourself is actually stay agile as opportunities come. Like, yeah, things change really fast, especially in our ecosystem, right? So keeping an open mind is extremely important, I think. Otherwise, I feel like, yeah, many of the hardware solutions would just get wiped out, especially like, you know, we don't change with the times. So. Cool.
Okay.
Oh, sorry. Yeah, you can go ahead and present. I apologize. I didn't realize I was still holding it.
Try and do this. We'll see if it goes back to me. Is this, can you see my presentation now?
Yeah.
Okay. So I started with kind of the most boring title that you could conceive of, which is efficient dot products. And I think it'll be more interesting than the title indicates. You know, back when I was asked to do this presentation, I wasn't quite sure what we wanted to have in this talk, but I kind of put in there the cross section of what I had been experiencing over the last few years and what I thought would be interesting to hear about. So you're going to get what that is. It may not be as DSP oriented as you like, but I think it'll be hopefully a little bit interesting and not too repetitive with what you've heard over the last few weeks. So, all right. So you guys probably know, but just as a little bit of review, what's a dot product? And it's given two vectors. You multiply all the elements element-wise, and then you add all those products together. And then if you want to know what matrix multiplication is, it's just a bunch of those things, right? You get two vectors kind of going different directions in your matrix, and you do the dot product of all those things, and you do that a bunch of times, and that's a matrix multiply. And as you know, or as your professors indicated you should know, if you have machine learning convolution, you can express that as matrix multiplication. We won't talk about how that works. That's an exercise that you should already be familiar with, or at least that you can do on your own. So if you write out matrix multiplication, this is kind of probably what it kind of looks like. You have, you know, kind of for each output, you have to do a dot product along the inner dimension. So you create your sum here, and it's you sum the products of all of these things. And so you see there's this dot product right in the middle of matrix multiply, and that's what we're trying to optimize. And so what do you get when you try and run this real fast? I need to figure out how to make this. There we go. Okay. So when you run it, if you actually compile this, if you turn it into valid C code and then you run it on your Cortex M4, which I understand is the development board that you have, this is the actual assembly code of your inner loop. So, and this is basically, if I can translate ARM assembly code into instructions, it's load from the A tensor or the A matrix and move the pointer by 1. This is called post increment in DSP talk. load from the B matrix. Look at that pointer that you post incremented and see if you're done yet. Move the B pointer to the next row here in green. Multiply and add. So you multiply the two things that you loaded, here R0 and R4, multiply them together and add with this other R1 value, put it back in R1, and then down at the bottom, you repeat if you're not done yet. And so this idiom right here, this multiply and add as a single instruction, is a very common idiom. In DSP, we call it MAC, or multiply accumulate. In some other cultures in computing, they may call it MAD for multiply add, or something like that. But this is a very common idiom, and so it's also common in architectures to optimize a little bit by including both the multiply and the add in a single instruction, since it's so common to see it in code. All right, so I don't know how to stop and really ask for questions, but I guess my first question is, has anybody gone and looked at the output of their compiler yet for what the inner product of a dot product might look like coming out of the ARM? And I don't know, is there a way to ask for hands up or something like that?
Yeah, the students can raise their hands in Zoom and it should pop up for you.
All right. So raise your hand if you've looked at the output of the compiler yet for what instructions you're seeing out of the compiler for a dot product. Anybody? That's not surprising, and that's good because then you hopefully won't be incredibly bored by the remainder of this video. Okay, now if you don't understand kind of these sequences and how this code and this assembly kind of work with each other, then raise your hand. Okay, so hopefully we're at a point where people understand what's going on. They understand the sequence of events. They can see how the code and the assembly work together, and they haven't seen it too much before, so it's hopefully interesting. That's good. Okay. Okay, so we have an issue here, which is that this efficiency here is not very high, right? We have this multiply add instruction, and in our core, that instruction, depending on how your M4 was actually built, that could probably go every cycle in the hardware. But in this inner loop, we have 5 other instructions in the loop, and again, depending on how you built your M4, those are probably also going to take some substantial amount of time to execute. And so I think that if I look at this loop, my guess is going to be that we're going to spend the majority of the time not multiplying and adding, but we're going to spend most of our time getting ready to multiply and add. And so if our goal is to do all this multiplication and all this addition, then we're not getting good efficiency out of this loop. And this is a common problem, and I'm not the only person who calls it this, but we typically call this problem feeding the beast. And basically, you can have a computational engine, and it's actually quite hard to keep that computational engine fed. And even a simple engine, like multiply 2 values and add it to a third value, it's easy to design processors where you have low efficiency, even for that kind of, single multiply and single add. And there are both software and hardware techniques that can help you feed the beast. And there's also a variety of ways in which this feeding the beast problem can arise. And so you can see this feed the beast problem in a variety of kind of levels, and we'll talk about some of those. But typically, if you want to keep your beast fed, you are going to have to work on it on the software side, and you're going to have to work on it on the hardware side. So this kind of gets to the question of what is a DSP? Well, a DSP is a processor much like an ARM or an x86 or any of these other processors. And it just has a little bit different focus. The goal of a DSP is typically that it's good at math or mathematically complicated, mathematically difficult tasks. And so it's really the case that in a DSP, we add features to improve the efficiency of those kind of math complex computations. And some of that is, you might find that there's a whole bunch of multipliers and, they can do fancy things like complex arithmetic and stuff like that. But often the extra features in a DSP are also there to help feed the beast. And the other thing about DSP is that we tend to put a lot of the burden on the programmer for keeping the beast fed instead of just having it done automatically by the processor. So a lot of these feed the beast features that you might see are things like doing your loads and stores in parallel with your math computation instead of doing them sequentially. And that's something that it's quite common for you to need to load data at the same time that you do your computation. So doing those in parallel is a way that we can help to keep the beast fed. DSPs commonly can do multiple instructions per cycle. They may have features like extra hardware to do loop computation, where it does the decrement, compare, and branch automatically in hardware. It may have fancy addressing modes to help you move the pointers around to where you want them. And so if we took that same loop that we did in ARM, here is our original ARM loop that you might get on an M4. And this is what it looks like on my DSP, Hexagon. We have our two loads, just like we did up in the ARM. And just like the ARM, we have this post increment, move the pointer by 4. You can see it's very, very similar in instruction. The syntax is different, but the instruction is basically the same. This instruction and this instruction are basically the same. This one is another load, but it has both the load of the data as well as moving the pointer. It can do that all in one instruction. And that's because in addition to being able to modify our address register by a constant value, we can modify it by a special register. And that helps us, in this case, to go down a column of data in a matrix where we don't have to have a separate add instruction here because we have this special addressing mode. And then this instruction is basically the same. It's a multiply and add. And then we have this, this thing that we can tag this packet with called end loop, and that does the decrement or comparison and branch. And it does it automatically for this group of instructions. The other thing is that these 3 instructions can flow down the processor and all be executed in parallel. And so all these instructions would be done at the same time instead of having to do them sequentially. So instead of having all of these instructions that are going to have fairly low parallelism and where you have to spend a lot of your instructions doing things like comparison and branch for the loop, we can set up the loop ahead of time and we can execute these 3 instructions over and over and over again all at the same time. Okay, so that's kind of an example of how in the DSP we have extra features to help keep the beast fed, right? We can keep our multiplier highly utilized by putting these instructions in parallel and having them be able to do things like move the pointers around in the way that we need. Okay, so any questions so far? I am having actually a substantial amount of confidence that I am not seeing whatever people may be doing. Does anybody have any questions? All right, so if you're developing software and you have an M4, you don't really you may not have the luxury of saying, I don't like that processor and I want a different one. You may be stuck, and you may have to have someone, someone may tell you, well, you have to fix it in software. And so let's look at some of the software techniques that we can do to try and improve the performance of the of this matrix multiply. And the first thing we might do is we might say, hey, let's unroll the inner loop. And this is a common software optimization technique. And some of the stuff that you have to do every loop, such as, you know, compare and branch back to the top of the inner loop, you can amortize that over a bunch of different operations. And so if we unroll the loop 4 times, let's say, this is what we get. And it's a bigger loop body, which you kind of expect. And there's a few things that pop out. We do see a little bit of improvement. Instead of 6 instructions per multiply, we get 20 instructions for 4 multiplies. So it's a little bit better. We get about 5 instructions instead of 6. We have mostly, you know, just like before, we have our kind of red instructions, orange instructions, and blue instructions that are the loads and the multiplies. And so we see mostly it's a lot of that, but we have these guys here. This one is a store relative to the stack pointer. This one is a load back from the stack pointer. This is called spill and fill. And it happens when the compiler runs out of registers. There's not a lot of registers available on ARM. And so the compiler is just kind of running out of registers in this case. And really, if we kind of look at all these instructions, we have 2 loads and a multiply, 2 loads and a multiply, 2 loads, and down here, that multiply. And really, it's going to be hard for us to do better than that, right? We have these we have this access and this multiply. And so 2 loads followed by a multiply is kind of required by the computation that we're doing here. So it's going to be tough to improve over 2 loads followed by a multiply. And so that's something that this style of optimizing in software is going to be pretty limited because we have to do this load and we multiply it once. Okay. All right, well, if unrolling that inner loop didn't work very well, actually we have one slide before that. So if we want to kind of draw out what we did, we took, in our big matrix multiply, we took 4 values in this direction in the A matrix. We took 4 values in this direction in the B matrix, and we're going to multiply and add those together, and those end up just going to 1 value in our result matrix. So you can kind of see that we do 4 things here. It's just computing the same sum, but then, and that sum is eventually going to go out into this value. Right? Single element in our output. Okay, so that didn't work so well. What else can we try? Well, instead of unrolling the inner loop, we can try and unroll this outer loop. And so instead of incrementing this by 4 every time, we're going to increment this by 4 every time. Because we're going to unroll 4 times. And instead of 1 accumulator here, we're going to have 4 accumulators. We're going to spit out 4 results after our dot product all our dot products are done. And we're going to do, we're going to work on 4 different dot products at the same time. And in this case, it's going to be the same element from the A matrix, but it's going to be 4 different values from the B matrix, right? And we can see how that works just because, you know, the I we're incrementing 1 at a time, the K we're incrementing 1 at a time. It's this J index that we're going to be incrementing by 4, and so that's the one over here that we're going to have to kind of unroll by hand. Okay. This is what we end up with the loop, and you can see that we only have this 1 load instruction in red. We have 4 of these loads in orange, which we kind of expect because we're loading 4 different things. And then we have these 4 multiplies and adds. And that looks nice. And we have our compare and our branch. And we go from 1 multiply for 6 instructions. We go to 4 multiplies in 12 instructions. And that's quite a big improvement, right? It's, three instructions per multiply, which is pretty good. And the key here is that we get reuse, right? We load this one value once, but we get to reuse it 4 times. And so that's really helping us out. And this loop looks, looking at it, it looks way better. You can see kind of how everything is used. There's not a lot of extra ads and stuff like that. It's pretty dense, and it looks nice. Okay. Well, so this one turned out pretty well, but let's see other things that we can try. Maybe we can try unrolling this outermost loop instead of the innermost loop. Before we do that, again, I have my picture here. So in this one, we're taking one value out of the A's, we're taking a bunch of values out of the B's, and that is affecting multiple values in the output instead of just one. Okay, so this is kind of how we're going through our matrix multiply. Okay. All right, so if we try and unroll the outer loop, we get one of these loads of our B matrix. We get 4 loads of the A matrix. So we do get reuse of the B value with multiple A values, but we see here we get the return of some spill fills, and the efficiency is not as good as our last one. It is, it's better than what we started with, but it's not as good as our last experiment was. And the reason for this, by the way, if you're curious, is because this A matrix, it's going down, we have to pull out values from 4 different rows, right? If we go and look at this, it's got 4 different rows, and it's harder for the processor to compute the addresses of the start of these 4 different rows than it is for it to just compute the next element. Because in C, if we have normal matrices in C, those matrices are row major. So all the things along a row are next to each other. That's what row major means. It's kind of next to each other. And so it's easy to kind of go to the next element in a row. It's harder to go from one row to the next row. Okay. So this is a little bit better than our original, but it's not as good as the previous experiment. Okay. All right. Well, we liked having reuse of the A matrix, and we liked having reuse of the B matrix. Let's try and, oh, I'm going the wrong way. All right, so let's try both, right? Let's unroll the outer 2 most loops. And so if we unroll the outermost 2 loops, we get something that it isn't very good, right? It's a little bit better than our second experiment, but it's pretty bad compared with our first experiment, right? Or it's worse than 3 instructions per multiply. It's a little bit better than 4 instructions per multiply, but it's not very good. And if we go and we look at why it's not very good here in this code that's so small that you can't read it at all, you'll maybe just have to trust me here. The problem is that there's so many accumulators here, right? This is 16 accumulators, and we don't even have that many registers available in our processor. And so there's so many accumulators that we need. There's not enough registers for us to do our computation. And so the compiler has to keep on loading and storing the accumulators to be able to hold all those intermediate values. And so this idea maybe isn't a bad idea. The problem is that the way our processor works, it's not going to work because we don't have the local storage in register file enough that is going to be able to let us do the computation that we want to do. Okay, so that idea was not good. Let's try something else. So what if we did that idea where we unrolled the outer 2 loops, but instead of going overboard and trying to do 4 elements in each direction, maybe we could do just 2 elements in each direction. And then we only end up with 4 accumulators, which is what we had before. And we get a little bit of reuse of this A values. We get a little bit of reuse of these B values. And so how do we do? And this is the code that we get. Kind of like we expect, we see 2 A matrix loads, 2 B matrix loads. We have our 4 multiplies and adds, compare, branch, just like we expect. And so we end up with 11 instructions for 4 multiplies, and that's the best yet. So we reuse the A and B values a little bit, and by reusing them a little bit, we don't run out of registers, and we improved on our experiment number 2, I guess, this one. This one here, we had 4 multiplies in 12 instructions. We were able to improve it a little bit by doing 4 multiplies in 11 instructions. So this is the best that we've done yet. And if we want to draw it out, it's kind of, instead of doing a whole row or a whole column, we're kind of just doing a 2 by 2 matrix as our kind of idiom that we're doing in the smallest space. Okay. So these are the kind of experiments that you can do in software when you're trying to optimize these kind of loops, and you can tinker around with how your computation is done. And as you try to reuse more, you can see that we had more register pressure. If you reuse less, then you get less register pressure from the accumulators, but you're also getting less reuse. So it's, we had to run these experiments and kind of tinker around a little bit to see how we could improve the efficiency. Okay. Any questions on fixing it in software? Oh, I see someone raise their hand. All right. Okay. So any questions about our software optimization techniques?
I guess one thing for the students that might be helpful here, Eric, is like, obviously, you're right about the number of registers, right? But I mean, if we look at the GPUs, I'm assuming even in DSPs, right? I mean, you usually have a pretty large register file, right?
Yeah. So like this inner loop, this experiment that we tried on a machine with more registers, this actually might have worked pretty well. But you got to kind of try it and see what's going to get spit out by the compiler before you can, before you really know whether it's going to be a success or not, right? And all machines have some limitations. So, things fit really well until they don't, and if they don't, then you can't use that experiment, right? So this wasn't saying that this is a bad idea to unroll both of these. It's just saying that when we tried this one that needed 16 accumulators, that didn't fit on this processor, and so we couldn't use this as a solution, right? So we had to dial it back a little bit.
Yeah.
Okay. All right. So so we did some work, and we were able to feed our little multiplier beast a little bit better. But where do those loads come from? And if it's coming from like a local cache that's local to your processor, or some local memory that's local in your processor, what happens if you miss in your cache, right? And typically, if you're loading out of your local L1 cache or small local memory, you should expect your loads to take a few cycles, and often there's stuff in the processor that kind of makes it very convenient when there's a nice cache hit, where you don't really even have to worry about how long it takes. But if you don't hit in your local memory and you have to go out to the big slow DRAM, that can be hundreds of cycles. And when that happens, especially on processors that don't have all kinds of crazy fancy features, you sit around and you wait and you do nothing. And so your feed the beast problems are not just about these inner loops and making sure that the values from your local memory get into your multiplier, but you also have to worry at kind of a different level about how you can keep your overall processor fed with the values that are needed, locally. Okay, everyone understand this problem? All right, so you can, again, turn to software and you can help the situation a little bit about using your local memory. And one of the problems that you would run into pretty quickly is if we go back to our normal loop, this A matrix we're going through in a horizontal direction, which in a normal C row major layout is going to sequential locations in memory. That's pretty great. We're going to get pretty good cache hit rates there. But then if you look at this B matrix, it's going to a different row every access. And especially if our matrices are large, this is likely to get lots of cache misses. And if our matrices get very large, you might see that it's, you kind of blow out your entire cache before you end up back going to the top again. And so this can be a disastrous thing to do. And so so the way that you can fix this in software is change the layout of your data. And so if you reorganize the data in this matrix so that instead of being row major, it's column major, then your Ks would be out on this second index instead of the first, and your sequential your access pattern would be sequential for both the A matrix and the B matrix. And so that's the kind of thing that you can change in software that may help you as you're doing this kind of computation, keep your data local. And for caches especially, but local memories kind of in general, you want to make sure that your accesses that are near to each other in time are also near to each other in address. And in caches, we call this temporal and spatial locality. And a lot of algorithms exhibit these kind of things. But also, the hardware says most code has these temporal and spatial locality features. But if you're trying to be a, optimizer in your software and make your software go fast on hardware, you need to help the hardware out by making sure that your code has temporal and spatial locality. Now, that's all great, but then the flip side is if you spend more time rearranging this data in this matrix than you would have spent missing on it in the cache, then you're going to be not going any faster. So you have to be careful that you don't spend all the time shuffling around the data if you're going to try and rearrange the data to make it amenable for the computation you're doing. So it can be quite tricky, but this is the sort of thing that you can expect to do if this is the kind of thing you're interested in. So in addition to making your data near each other, a lot of processors have features to get your data early so that you don't miss in the local memory. And first one, if you have a processor that has a cache, is something called prefetching. And prefetching is a hint to your processor that says, hey, I'm going to need this chunk of memory in the future. Please bring it into the cache so that when I go touch it in a little while, it's already there. And some processors do that automatically in hardware by adding a bunch of fancy features. Sometimes, and you could probably guess that this is what we do in a DSP, is we have instructions and we make the programmer or the compiler tell us ahead of time what it's going to need in the future. That's trickier to do, but that's what we make the programmer do. And it can be tricky to get right and to tune the performance. Just as a kind of example, if you do your prefetch not far enough in advance, then it's not going to be back in the processor yet by when you need it. If you do it too far in advance, or you do too much of it, it might bring it into processor and then evict it again because it needed more memory. And so it might get kicked out before it's ever used. So it requires careful tuning, and it can be very tricky to get right. And the other thing is, for prefetch, it tends to be very invisible. So the only thing that you can observe is that your performance gets better or worse as you're trying to tune the prefetch. The other kind of technique, which if you draw it in a picture looks kind of the same, but is quite different in practice from a programming model, is if you have local memories, you have a DMA engine. DMA is direct memory access, but basically it moves around memory. It copies memory for you from one place to another. And so you'll copy memory from like a large external DRAM into your local memory, and you'll tell some engine to go do that, and you'll wait for that engine to be done. And so that's very much managed in software. It's very much something that you observe, right? You have to make sure that you go program it to do something and it actually changes memory values. DMA engines and local memories tend to be kind of hard to abstract by the operating system. And if you run out of local memory storage, it's very, very painful. Whereas if your cache is a little bit too small, you just get some performance problems. So local memories are common, but there's trade-offs. It's simpler in some regards, but worse in others. And so, you know, these are kind of two ideas that are similar conceptually, but you know, very different from when you actually have to program them. Okay. All right. Any questions about kind of from a Cortex M4 like a type of processor, like there's things that you might need to do to keep that beast fed?
Is there anything fundamentally different that one would imagine doing on like the microcontroller based sort of ecosystem, right? I mean, I think like this I'm kind of thinking in the general context of, you know, bigger systems kind of makes sense. I'm just kind of curious.
So I think everything that we've talked about up to this point is stuff that you would be doing and probably are doing in the libraries for even very small systems. So even very small systems, you need to keep your data local. You need to, you know, squeeze as much performance as you can out of your small core, out of your small engine. And so, you know, all of the kind of stuff that we've been talking about here for the most part is stuff that you would kind of expect to do even if kind of all you have is a Cortex M type of core, something very low end. Okay.
Is anything like different because like let's say we have Flash versus like just relying on DRAM, like just kind of thinking about the access latencies are all quite, right? And then you have like different caching structures for microcontrollers than you would in a traditional.
Right. Yeah. So here I wrote DRAM, but this kind of concept would be the same if it were Flash, right? If you have some external Flash stuff, you if you have to go touch that Flash, you're either going to wait a long time to go get that value, or you need to bring it in way in advance. And if you bring it in advance, how are you going to do that? It's either going to be from a prefetch, or it's going to be from DMA. If it's DMA, you have to have some local memory where you're going to put those values. And so, you know, kind of the you know, I wrote DRAM here, and that's kind of what in our processor we tend to think of as the slow thing that's far away, but this could be, you know, DRAM or Flash or tape or stone tablets or whatever other slow storage. You know, you need to go get that information and bring it to a faster place that you can access it. And you have to do that ahead of time if you don't want to sit there and wait for it.
Yeah, except like, I mean, in the microcontroller space, right? Like you're not going to have like hardware prefetch engine and so forth, right? Like, so from that sort of a perspective, would you say that in this ecosystem, it's going to be much more aggressively based on the software, like, you know, just the loop restructurings that we would do in the compiler?
Yeah. So you know, different microcontrollers, and you know, what is a microcontroller is kind of a, you know, it's a changing thing, right? It's very common now to have 32-bit microcontrollers, which would have been, you know, shocking not that long ago. I would say that this is more likely a more likely model for a microcontroller, and you'd probably replace this DRAM with Flash or, you know, ROM or something like that. And you would have some amount of local memory, and that local memory is probably quite precious in the amount that you have. That's more common in the embedded space. That's definitely, I think that would be definitely true. Yeah.
Mm-hmm.
But you know, conceptually, it's you know, whether you're at this low microcontroller area where this is Flash and your local memory is, maybe 32K or something like that, and your CPU is very, limited in the amount of performance, or whether, we go to some of the things where we're scaling up, which is what we're going to talk about next. And this has, 1,000 multipliers in it, and this is, DRAM that's fairly high bandwidth, and this connection here is very big, and this local memory is quite a bit bigger. Like, conceptually, it's the same, right? You have to bring the data from the slow thing into the fast thing before you need to use it, or you're going to be waiting around, right?
Mm-hmm.
So, all right, so we did kind of the best that we could. We wrote some low overhead software. We reorganized our data for locality. We pre-fetched our data. But if you need more power, then, and you're at the limit of what you can do in software, you have to change the hardware to go faster. And so we talked about kind of at a low end, the things that we can do to go faster. Now we're going to talk about the things that we can change in the hardware to go faster. All right, everybody ready? All right, so the first thing that processor people do is they do vectorization, which is sometimes called single instruction multiple data. And if you've been using any processor that's kind of been made in the last 20, 30 years, well, maybe not that long, 20 years, they have some sort of extension to their base architecture which supports these kind of single instruction multiple data things. And basically what they have in common is they typically have wide special registers that hold a bunch of elements, and then they're going to do the same thing, same operation, or some similar operation on every element in the in that large vector that has many elements together. And if you go and you kind of survey different processors and their extensions, you'll see vector sizes that kind of go from 64 bits to maybe 1024 bits. And so, depending on how much hardware you want to throw at the problem, you get wider or narrower vectors. And there's a whole host of different algorithms that are amenable to using this single instruction multiple data. Different features of your single instruction multiple data architecture will give you kind of different abilities to do various algorithms. So this is a very common technique. And so if we
Eric,
take
just to jump in really quick to give you a 10-minute time check.
Oh, is it 10 minutes left?
Yes.
Oh,
no,
okay.
No need to rush you or anything, but yeah.
Well, I need to keep going. So here we would take our normal loop that we did. This is the experiment number 2. And instead of having our elements, we're going to load our elements in kind of a vector load. So we load 4 of them at a time. And then we have a single instruction that does our multiply and add. And that would be kind of a classic vector multiply and vector add, or vector multiply and add. And that's how we would turn our kind of unrolled loop into a vectorized loop. So that's great. We made some improvements. We reduced the number of multiply instructions, and we reduced the number of load instructions. And if we had even larger vectors, we could get even more savings. And that's great, but you have to watch out for Amdahl's law. And it says, as you make your computation go faster and faster, the other stuff that doesn't get faster will start to dominate. And so if you speed up half your program, doesn't matter how much you speed it up, it's going to only get twice as fast at most. So that's something to watch out for, is that you can keep on adding features to your architecture and to your machine, but the more that you add, the more difficult it becomes to feed the beast. And those feed the beast problems return, right? So now you have your new fancy vector engine. Now, how do you feed that new vector engine? And if if you're processing that data a lot faster, it means you work through your local memory a lot quicker. So as a question, if you're working on 256 bytes per cycle, you have a 16K L1 data cache, you're going to go through it quite fast, right? That's 64 cycles to just go through the entire cache. So the wider your vectors are, the more memory you need to feed them. And you definitely don't want to try and get all that from external memory. It's going to be too slow. There's also more ways that you have to worry about feeding the beast as you get bigger. You have to feed the beast with data, but you also have to feed the beast with power. And so, you know, you have to worry about where is all your energy coming from? How can you dissipate the heat? How much is it going to drain? And your budget is not necessarily all that big. If you have a phone, and the phone is, I mean, that's how Qualcomm makes all its money. That's who I work for. You know, your entire power budget's about 3 watts, because otherwise it makes your phone too hot. And if you do 3 watts, your battery's only going to last about 2 hours. So you don't have a huge power budget here to deal with. So as we're designing, and as we want to make our hardware faster and faster, we need to be more and more frugal with energy. And so there's a bunch of things that you can do to be frugal with energy, but one of them is that you need to avoid going to DRAM because it's quite expensive from an energy standpoint. And you really don't want to do, you really don't want to go to SRAM that much, because even SRAM is quite expensive from an energy standpoint. Reading 64 bits, which would be the input to two 32-bit to a 64 bits of data goes into a 32-bit multiply, takes 20 picojoules, and then you know, compared with multiplying those values as 3 picojoules and adding them together is almost nothing. So we need to reduce the amount of memory reads, and we need to reduce the amount of data movement. Okay. So if we wanted to continue on this dot product road, we can unroll both of these outer loops like we did before. Vectorization was adding features to do unrolling in one dimension. If we do unrolling in both dimensions, we can get more reuse, right? So instead of just unrolling one of these, we can unroll both. We'll have an array here that will multiply this vector times this vector, and we'll reuse this data this amount of times and this data this amount of times. Okay. So if we do that, we read each piece of data once. As we go through our 2 input matrices, we accumulate those products in this kind of array of accumulators, and we get a lot of reuse of the data. And this idea scales up. Both you can use this kind of primitive to compute very large matrices, and the hardware can scale up to larger arrays. So keep going. Take a little bit of a digression. You know, as we try and design things to go faster and faster with dot products, you start to run into these we call them squeezing the balloon problems. That you can make a specialized piece of hardware for these dot products, but it's going to stick out other problems. So if you do more reuse, you're going to get a lot more accumulators. That's going to be higher cost. You're going to get more overcompute because things don't maybe fit exactly in your array, but you get lower bandwidth to local memory. That might be good. If you have bigger local memory, it's going to cost more energy per access, but you can keep your performance up and you can go to DRAM less. So these kind of trade-offs are sometimes hard to design for, and there's a bunch of different factors that go into figuring out what you need to do for them. The other thing, especially as we're getting to this point where we have these multiplier arrays, is kind of choosing between versatility versus efficiency from specialization. So if you have a multiplier array, it's great at doing matrix multiply. That's all it can do. Whereas a vector architecture that has a kind of bunch of instructions that can operate on vectors, there's actually quite a lot of algorithms that can help you compute. So that's another trade-off that you get. But if we assume that we want to keep going on this idea of multiplier arrays, this is really good for doing matrix multiplies. If you want to continue being frugal with energy because you're energy dominated, you can go away from even 32-bit integers, definitely go away from floating point and go to low precision integers. So as we talked about right at the beginning, If you go with 8-bit integers for your multipliers, it's quite a lot less expensive for power, and it's a lot less expensive for the amount of area that it takes on a chip to do that multiply. DSP people, we typically call this integer arithmetic fixed point, because you can do either integer or fractions. And again, it's pushing a lot of the complexity to the programmer, and not all algorithms map well to fixed point. Some of them require a large amount of dynamic range, and for that, you kind of want floating point where you have this exponent that's pretty handy. But it's way more efficient. So if you read Charles Dickens, you read The Christmas Carol, right? Scrooge liked darkness, right? You would probably also like fixed point because it was cheap. And so that's the reason we like it in DSP also, is because fixed point is really cheap. All right, so let's invent an accelerator real quick. Your marketing people say they want a Teramac. You think you can go a gigahertz, and you're very power constrained. We're also time constrained. I apologize for managing my time budget quite poorly. But so if you think you want to go at a gigahertz, you divide a Teramac by a gigahertz, and you need 1,000 multipliers per cycle. They say, okay, well, if I want my array to be roughly square, that's 32 elements times 32 elements. You're going to choose 8-bit values going into your multiplier array for low energy, and you need an A element and a B element every cycle. So that's 2 inputs per cycle. Each of those are going to be 32 bytes, right? 32 times 1 byte per 32 elements times 1 byte per element. And if we go back up and we look at that big table, we saw that there was a 32K SRAM that we could use. We're gonna need 4, and it gave you 64 bits. We're gonna need 4 of those to equal our 32 byte access. And that gives us 128K. And that's actually, let's say that's a decent amount for our A memory and our B memory that can hold the data. And so this is what our accelerator is starting to look like. We have an A memory for one matrix, a B memory for the other matrix, a big 32 by 32 multiplier array. And if we go and we compute the power it's going to take, our reads are going to take 160 picojoules, because each access for each little sub-memory is going to be 20 picojoules. Our multiply and adds are 0.3 picojoules each. So we got 1,000 of them. So that's going to be 307 picojoules. And so we spend about 65, about 2/3 of our power in the actual MAC array. We spend 35% of it or so in the SRAM. We get a total of 467 milliwatts using our table before at a gigahertz. And that's not bad. And so because of that reuse that we get from the data, we ended up having our memory not dominate our power. And we were able to do this. All right. I see something popped up as a poll. All right. So we invented our accelerator, and now you know the basic concept for a whole bunch of startups. So you take this slide deck, go take it to a big company and ask them for a few $100 million. And they all kind of look the same. So that's and the reason they look the same is because the things they're trying to compute are about the same, and the ways that you solve the problems that naturally arise have kind of similar solutions, and that's why they all kind of look the same. All right, I think we're probably out of time. There's a section in here that you should look at called the shame of computer architecture. Basically, nothing has happened in the last 30 years from a big idea kind of standpoint, and that's not necessarily a bad thing. Kind of 2 things that you can take from that. One is that new ideas could be revolutionary in the industry. The other thing is looking at old things can help you solve new problems. So that's it. Sorry for having to rush at the end. I didn't budget the time very well.
No worries. All right. Thank you, though. For the folks who can stick around, that would be great, because I'm going to ask Eric about some more qualifying questions.
Okay.
Please fill out the poll for your attendance. Eric, one question I have for you, specifically in the context of what you're getting at here, right, for architecture. Like, I'm curious, what do you see specifically in the TinyML kind of space? Like, is there something new that we'll see, or really no, it's pretty much the same old thing. We're just gonna hammer this thing out, and that's about it.
So at the tiny space, I think it's going to be, well, a couple things. One is, I think there's going to be a natural pressure for how much performance can I get versus how much power can I spend. And so I think there's going to be if you have an M4 this time, you're going to be frustrated with the types of models that you can do and the performance you can get on an M4. So you're going to be demanding more performance. So at the same time, you're not going to want to invest much more in the power that you're going to want to spend on these TinyML models. And so, doing these sort of techniques to try and boost the amount of performance that you can get while not boosting the amount of energy consumption you get are, I think, going to really be very important for the embedded space.
Do you see anything from the kind of models that we're talking about as compared to like the stuff that we've done on mobile systems? Like, do you see anything different that you think will be coming around because we're interfacing more with sensors? And is it really just going to be, I mean, if it's vision, I feel like it's pretty boring, honestly, I think. Thing to death, and yes, there'll be more. But with like the fact that there are so many sensors out there and so many different kinds of sensors, I'm kind of curious, like, is there something new that'll come out because there's fundamentally different input source that we're not used to looking at?
Yeah, I mean, people find all sorts of clever things to do with the sensors that they have, right? So, like you take an accelerometer, right? If you take an accelerometer and the data rate that you need to read off an accelerometer for waving something around with your hand is actually not that much. But, and then if you can process that signal stream and classify different things, right? There's all sorts of toys or input devices or things like that you could make out of that, right? Like my kids love Harry Potter, right? And like, why isn't there something that has a Cortex, a little M core in it, and the accelerometer where they can wave in different ways and it, cast some spell using this toy wand, right? Or, you have your controller for your Wii and it has a gyroscope in it, and it, like you should be able to have like sword fighting thing where it understands the motions that you're making, and it does those. And so, just a little accelerometer or a little gyroscope and the ability to classify actions regardless of who the person is that's waving the stuff around opens up a whole bunch of different types of things that you can do that previously were kind of infeasible to do. That's accelerometer. You think of microphone. There's all sorts of things that you can do with a microphone if you can, listen very well. And we've started to see those with, little hubs that sit around. But, the more types of things that you can read in, the more interesting things that you can do with them.
Yeah, this is like one of those interesting spaces where I feel like the possibilities seem endless, but it's like we got to kind of wait it out. It's like you provide the building blocks and then you say like, okay, well, someone's going to unlock it. It's like, This is where I tell students and everybody, it's like the reason I think the TinyML space is so interesting is it's like that time when the phones came out and like you suddenly, you have a nice operating system where you have some sort of nice base, the software and the hardware kind of evolved to the point where actually you can write an interesting application without knowing too much stuff. Of course, you still got to learn something, but in this case, learn about some frameworks or something. But the integration with the sensors and the hardware being able to do this and the interest in the industry to support this, all of this is kind of like converging to this point where I feel like it's sort of like this next major gold rush ahead. The devices are dirt cheap. They're completely accessible across the planet now.
Yeah.
It's no longer like you just do, let me train the model and then that's it,
Yeah.
The time you do machine learning, that's all you can do. Right?
Yeah. And, that's, I say that, I really like the stuff that we do building machine learning stuff and the firmware and the optimization. But most of the people that we talk to out of school, and I think probably for good reason, aren't as interested in that. They're interested in solving new problems with machine learning. And that's probably where most of the value is, right? It's like we're kind of the compiler for the language, or the runtime for the language. But most people don't want to work on the compiler. They want to use the language to solve interesting problems. And so that's not what I do, but I understand that that's what most people want to do. And so that's I think good. And there's all sorts of cool things that people can figure out to use these fairly simple sensors and fairly simple ways to classify things.
Yeah. One thing that's been really nice witnessing is, Pete and I are also doing the edX version, the online version of TinyML, and it's like pretty interesting because people come in with such a clean slate. They haven't been polluted yet because this is their first foray into machine learning, and because of that, they have like these real world application situations that they think TinyML is going to solve, and I feel like that's the most interesting thing because people like us in this class are already kind of polluted because we got to know the space, so you're kind of like looking at it through this one kind of lens, you kind of pre-bake some lens, and they seem to just kind of come at it like a completely new. I think that's really interesting. Is having people look at it through, being naive is sometimes a great thing.
There's a lot of problems out there. So if I could go back to this slide, right? This is kind of from a hardware standpoint, we haven't really had much in the way of really great new ideas in the last 30 years. If you look at kind of a software programming language, things were pretty much the same. If you start with Fortran or C up until, around here, and then we got a new tool in our toolbox, which is these, machine learning networks and the ability to train them in a nice environment and all that sort of stuff. And that's really taken off in the last, 5-6 years. And it's given us a new tool in the toolbox that's very exciting. And so from a hardware perspective, we don't have that much in the way of new ideas at the current time. From the software perspective, we have a new tool that's machine learning. And that's, I think, why there's so much excitement in it, is because it's a new tool in the toolbox that can solve problems that a while ago were nearly impossible to consider solving, right?